There are times when more than one valid Lewis structure may be drawn. So for example, let's take the nitrate anion. Nitrogen comes in with 5 valence electrons. Each oxygen has 6. We have 3 of those. And then we have 1 electron for the charge. So we have a total of 24 electrons for this molecule or this molecular part. So we draw our skeletal structure and then we fill in the electrons on our outside or our attached atoms. And then we've used up all 24 electrons. So now we have to correct for our central atom. And in order to correct for our central atom, we're going to drop one of these pairs of electrons into a new pi bond so that there's a double bond. But why would we drop those when we could just as easily drop these electrons? Or we could drop these electrons. All 3 of these are valid structures. And we draw them this way. So we draw all 3 of those structures with a double-headed arrow between it. And because it's an ion, because we have an anion here, we give it square brackets and we put the charge on the outside of that bracket. These are called resonance forms. Resonance. In order to have resonance, you have to be able to trade the position of a lone pair of electrons and a pi bond. You see the pi bond goes from the oxygen on the left to the oxygen on the right, and then moves to the oxygen below. So when we have resonance structures, what we're showing is that there's more than one position for that lone pair of electrons to be. It could either be a lone pair or it could be a pi bond. In reality, we have what is called the resonance hybrid structure. So we would start with our skeletal structure and then we would give partial pi bonds to all 3 of the oxygens. And that way, what we're showing is that all 3 of these potential Lewis structures are valid, and they all contribute equally to the resonance form. One way we can tell if our Lewis and resonance structures are valid is with a quick calculation of what's called formal charge. Now, the formal charge of an atom is a hypothetical charge that the atom would have if we could redistribute the electrons evenly between the atoms. So for example, if we have carbon monoxide. Now carbon monoxide, there's 4, there's 6, we have 10 electrons each. We're going to distribute our electrons thusly. So we have 2, 4, 6, 8, then we have 10. 2, 4, 6, 8, 10. 10 electrons total, but we have to share. We have to share because we don't have enough electrons to not share. So we're going to form 2 pi bonds here, and we're going to end up with a structure that looks like this. Now, in order to have this structure, each of these atoms is going to calculate that formal charge. We start with the number of valence electrons each atom brought in. Carbon brought in 4, oxygen brought in 6. Now altogether, the molecule is not charged, but each atom individually is going to hold a formal charge. Then we're going to subtract the number of bonds that the atom is participating in. Carbon is participating in 3 bonds. Oxygen is also participating in 3 bonds. Then we're going to subtract the number of non-bonded electrons. This is not the number of pairs, this is the number of electrons. Carbon has 2 non-bonded electrons. Oxygen has 2 non-bonded electrons. So the formal charge on carbon in carbon monoxide, when it's drawn this way, is a -1. The formal charge on oxygen when drawn this way is a +1. Now, most of the time when we have a molecule, it's going to be more favorable for all atoms to have 0 charge. If there are non-zero formal charges, then the arrangement of the smallest non-zero is preferred. So if we have multiple atoms and one of them has like a +3, not going to be a preferred case. It's also preferred when adjacent atoms are either opposite charged, like these are, or have a 0 next to them. Now, when we can choose, it's always best that the more electronegative atom carries the more negative charge. In this case, we can't choose. Oxygen isn't terribly excited about being a positively charged atom, but it is capable when it doesn't have a choice. Now, let's look at the bicarbonate ion. Bicarbonate looks like this. And bicarbonate has a structure that looks a bit like this. This oxygen has 2 lone pairs. We have a double bond here. And this oxygen has 3 lone pairs. Now, because it is an anion, we have to give it square brackets and give it a negative charge. Now, it would have been just as valid to draw this structure with the double bond on the other oxygen. So what we're showing with these 2 structures is we are showing the movement of this pi bond and this pair of electrons, which becomes this pi bond and this pair of electrons. So we're showing a resonance form. Now let's calculate some formal charges. If I number these atoms, and I will number them, or the oxygens rather, I'm going to number. The carbon is fairly self-explanatory, but if I number the oxygen atoms thusly, then we can calculate the formal charge. So I have oxygen 1, oxygen 2, carbon, oxygen 3, and I'm just going to go through the motions to calculate the formal charge. So like before, we start with the valence electrons. Each oxygen comes in with 6 valence electrons. The carbon comes in with 4 valence electrons. We're going to subtract the number of bonds the atom participates in. Oxygen number 1 has 2 bonds. Oxygen number 2 also has 2 bonds. A double bond counts as 2 bonds. Carbon is participating in 4 bonds. Oxygen 3 is participating only in 1 bond. So far we have this going for this molecule. And similarly, we'll do that for the second molecule. Oxygen 1, oxygen 2, carbon, and oxygen 3. So now we're going to subtract the number of non-bonded electrons. Now this is not the number of lone pairs, it's the total number of non-bonded electrons. So oxygen 1 has 4 non-bonded electrons. Oxygen 2 also has 4 non-bonded electrons. Carbon has no non-bonded electrons. But oxygen 3 has 6 non-bonded electrons. So that means oxygen 3 has a formal charge of 1 in this case. In the second Lewis structure that we have here, we have 4 for 1, we have 6 for 2, carbon still has none, and oxygen 3 now has 4. So you see the charge moves in our resonance structures. So let's do one more example. Here we're going to have CSN, and it's an anion. So what is the Lewis structure? Well, in order to find what is the Lewis structure, we need to see what can we do with this, okay? Carbon comes in with 4, sulfur comes in with 6, nitrogen with 5, and then we have 1 for our charge, 1 electron. So we have a total of 16 electrons to distribute around this molecule. But in what order do these go? Do we have carbon, sulfur, then nitrogen? Or do we have carbon, nitrogen, then sulfur? Or maybe nitrogen, then carbon is in the middle, and sulfur. So we need to calculate the formal charges on all of these atoms to see which is going to be the most likely Lewis structure. I'm just going to try to fill in all of these electrons quickly. So we start with the number of valence electrons. We have 4, 6, and 5. 4, 5, and 6. 5, 4, and 6. Then we're going to subtract the number of bonds. Now we subtract the total number of non-bonded electrons. And remember, these are only the non-bonded electrons on the atom of interest. So in this column is carbon. So we're going to subtract 4. And sulfur has none. So we see on this first example, this first structure, we have charge separation, a -2, a +2, and a -1. For the next one, we have a -2, a +1, and a 0. And for the last one, we have a -1. Given the previous qualifications before, it's most favorable that all atoms have a 0 charge. We don't have that option here. Next, if there are non-zero formal charges, the arrangement of the smallest non-zero is preferred. Each of these Lewis structures has a 2, and this one does not. So this is going to be the preferred Lewis structure because the arrangement has the least amount of charges, least amount of non-zero charges. It's also preferred that when adjacent charges are not 0, they are opposite. Now, we do have the opposites, so that would be okay, but we've already decided that this is going to be the most likely Lewis structure for this anion. So we would put it in square brackets and make sure the charge is outside those square brackets.